talk about measures of spread, the key idea here is standard deviation. We'd like to define variability. One way to define variability is to take the biggest value in a set minus the smallest value. That difference doesn't tell us much about the shape of the distribution, but it does tell us something about its spread. A different plan is to measure variability around the mean. We need to figure out a way to quantify the variability around the mean. And to do this, let's look at our Python notebook on the measures of spread section. Let's look at a simple example of a collection of 4 items in order to describe the spread of the data. Here we've got the array with the numbers 2, 3, 3, and 9, and we'll put this into a table called SDTable and display it. The average value of these numbers is 4.25. We saw that earlier in the lectures. The deviations are the differences between the values and the average value. So if we take the values that we have here, 2, 3, 3, and 9, and subtract off the average value, we should get an array consisting of the deviations. We can make a new column for our SD table and consisting of the deviations. There we go. Notice that a number like 2, which is lower than the actual average value, has a negative deviation, and a number like 9, which is higher than the average value, has a higher deviation, a positive deviation. The deviations themselves sum to 0, always. That's a property of the way that we computed them. So you can't really use the deviations themselves to decide about the spread. On the other hand, excuse me, you could look at the squared deviations. And here we'll just add an extra column to our table consisting of the squared deviations. The squared deviations are, of course, always bigger than or equal to 0, and so the sum of those squared deviations is a good way to measure the measure the spread. On the other hand, you could have a lot of sum of squared deviations, if not because you had a lot of spread, but because you had a lot of observations. We'd like to kind of factor out the effect of having a lot of observations, and one way to do that is to take the average value of the average value of the squared deviations instead of just the sum of the squared deviations. So let's take the average value, or the mean, of those squared deviations in our table, and that value has a special name. It's called variance. So the variance is the mean of the squared deviations. The units for variance are a bit odd. If the units for our values were in weeks, then the units for the deviations would also be in weeks, and the units for the squared deviations would be in weeks squared. And that means then that the variance, which is the mean of these squared deviations, would have units weeks squared as well. That's a bit unfortunate. It's hard to interpret what that number would mean. And so in general, we like to take the square root of the variance and report that number. That number has the benefit of being of having units which are exactly the same as the units of our original values. So if we take the square root of the variance, we get a number whose units are weeks, and the square root of the variance is called the standard deviation. The standard deviation is the square root of the variance. It's an important thing to remember. The standard deviation here is 2.77. You could interpret that as 2.77 weeks, or if, as is here in our notebook, if the values were prices in dollars of jars of pasta sauce, then the standard deviation would be $2.77, telling you something about the spread of the prices among these 4 jars of pasta sauce. You can also use the np.std, np.standard deviation command to get the standard deviation directly from an array. Here the values variable is storing the array of values given in this column here, 2, 3, 3, and 9, and we just apply the np.std a command to values, and it gives us the standard deviation directly. Let's just summarize where we've been so far. The standard deviation measures roughly how far the data are from their average. It's a measure that tells you something about the spread or the variability of the data. The definition of the standard deviation is that it's the root mean squared of deviations from the average. That means that it's the square root of the mean of the squares of deviations. That's a complicated thing, and we can compute it all in one command using the np.std command in Python. The standard deviation has the same units as the data, which lends itself to interpretation. Standard deviations give rise to a notion called standard units. If you're given a collection of values and a particular value in that collection, you might be interested in how many standard deviations above the average is that value. Here's a way to calculate that. You start with your value, you subtract off the average of all the values in your collection, and then you divide by the standard deviation of your collection. That will give you a z-score, which we call the standard units for your value. A negative z-score indicates that your value lies below the average. A positive z-score indicates that your value lies above the average. And z equal to 0 tells you that your value is exactly equal to the average. When values are in standard units, the average z-value is 0, and the z-value corresponding to one standard deviation is 1. That's why we call them standard units. The Russian mathematician Chebyshev showed that irrespective of what the collection of values are that you start with, values of your standard units are always between -5 and 5 standard units. Let's move over to the demonstration to have a look at standard units. So standard units are used to express how a single value relates to the rest of the values in the collection. We obtain the standard units for a value by subtracting the mean value and then dividing by the standard deviation of the collection of values. The center is 0 in standard units, and a value that's 2 standard deviations above the mean has standard units of 2. Here's a function that converts an array of values to an array of standard units. I've called the function standard units. It takes an array x and it returns this array, which consists of the standard units. Let's look at our table consisting of birth data. Look at the column of values consisting of maternal age and make the array ages. And then let's apply our standard units function to the array ages to get ages standard units. Then we'll put both the age in years and the age in standard units into a table called both. Here's that table. You can see that 27, a mother with age 27 in years has very small negative standard units. That tells you that 27 lies close to but below the average for the average age of all mothers. On the other hand, a number like 30 lies above the average, and you can see that here because the age in standard units is positive. After converting to standard units, what are the mean and standard deviation of the sample? Answer this before running the next code block. Well, the average age in standard units is 0, and the standard deviation of the ages in standard units is just 1. We've standardized the standard deviation to be 1 unit away from the average. In the next two cells, we'll explore how shifting to standard units changes the histogram of the maternal age data. Here's the ages in regular years. We see that tailing off to the right. And here's the histogram of the age in standard units. It should look exactly the same as the histogram for age in years. The only thing that's changed are these units here on the x-axis. Shifting to standard units changes the units, but not the shape of the distribution.